any complaints? Yes? Can you speak up?
You insisted a lot on the Z being present or no.
Yes.
Usually Z is somehow say it's 1 by changing some factor. So what is different here? Is it because we're out of equilibrium?
Well, it depends what kind of science you do. So if you are doing disorder, then Z is not 1.
We can never set it to 1.
I mean, you can send it, normalize it to 1 probably in one specific disorder realization, but then you keep this normalization and you change disorder and Z changes. Right? So then you,
And then you average over all of them, so that's where the problem is.
right, then you have to average all of them, and you have to acknowledge that once you average something, there is a denominator in this something. So you have to average upstairs and downstairs simultaneously, not separate. And that's a problem. And that's why supersymmetry, replica, and hundreds and hundreds of good people, bang their heads. Yeah. And here we are free of this, in a very good shape. And that was realized in early 80s, actually. I think Heinz and Polinsky was the first who sort of said this, and then many other people used since then. Yes?
So this has to do with the section you asked us to glance over before we came.
Yep.
So that's the section where we calculate the Green's function.
Yep.
And I wanted to ask, why is rho infinity still sitting in the Green's function?
Why not?
Why is rho minus infinity, which is the rho at the density of the density matrix at the infinite path, still
Right.
sitting in the Green's function?
It does, because we are doing sort of idiotically simple example.
I see.
It's a harmonic oscillator, which there is no interaction, there is no chaoticity, nothing, right? So there is no equilibration, thermalization. So this information simply propagates all the way through. But in a sense, it is artificial. But the fact that something is sitting there is indicative.
Okay.
You'll see. All right? More questions? Complaints? I'm serious. Suggestions? Should I go faster, slower? Okay. I take it as if I'm doing okay. All right. So, but we're almost done for a formal construction, and we'll start hopefully soon doing a little bit more interesting things. So far what we have achieved, we write 1, and we call it Z. And we write it as a function of integral of phi bar phi. And this is an action, which is a functional of these two. And then in a slightly dumb continuous notations, this thing can be written as integral over Heldish contour dt phi bar t Green function. And I'm maybe screwing up factors of I, so excuse me for that. Or if you introduce separate notation for field leaving here, you call it phi plus, field leaving here, you call it phi minus. Then what you got is a familiar integral from minus infinity to infinity dt, phi plus, plus and minus the same for phi minus. Now that's in a sort of short and appealing notation, but as we mentioned towards the end yesterday, it's dangerous because this operator in a sense is not well defined in the sense that it has a zero mode. And we have to get it sort of take care of it. But our original green function, as you remember, was nothing dangerous. It was simply big matrix with minus ones here. Here, one here, and this H minus, plus H plus. Zero everything else. Right? And that thing was invertible. Now, why on Earth I want to invert it? Because what we will actually need are correlation functions. So if I want to calculate correlation function of IT phi bar T prime, and in principle each one of these T and T prime can be leading either on forward or on backward contours. So I have actually 4 possibilities hidden here: up, up, down, down, up, down, down, up. So this thing is nothing but simply Gaussian averaging of phi T prime, which is the same thing. Right? So anytime we want to calculate correlation function, which is defined like this, at least in our Gaussian model, it's nothing else but inverse of this quadratic form sitting in the edge. Again, trying not to screw up factors of I, this is I times G with the labels T and T prime. Okay. Or this, instead of those two, you can think about discrete labels J and J prime. Each one of them is running from up to 2s. Okay, so we do need to invert this matrix, and it's not a big deal because we already calculated the determinant of this matrix in one line. And to know the inverse matrix, you, in addition to determinant, you have to calculate what's the negative minus this matrix. You can do it with the same algebra. Or alternatively, you can just give this 6 by 6, 8 by 8, whatever matrix to mathematically, it will do it in half a link. And then you look at the result and you try to identify the pair. And there is this bulky expression 232 in my notes, which is a result of this mathematical inversion of the matrix. Right? So now you look at it and you immediately can generalize it to any n. The pattern is completely clear. In particular, what you notice, just looking at this pattern, is that some elements contain this, as was just asked, distribution function. Some do not. And then another thing that you can spot there is that there is something special about diagonals. The pattern below diagonal and pattern above diagonal is not the same pattern. Right? And again, it's all sitting here. Now, then you can go to immediately to continuous representation of generalization of this thing. Pretty much in the same way we already did by calculating determinant. For example, if you see something like H minus in the, sorry, remind H minus plus 1 minus plus R on the non-T. Or again, maybe signs are wrong. That's not the point here. So if you have this, then you have to say that this goes to 1, because what you will have after the exponentiation, you will have delta t squared, and only 1 power of n here. So that goes to 1. But if you see something like h minus plus whatever to the power j, you should say that this is either plus or minus I omega naught delta t j. And this thing you identify as the time. So this is your time t, or time t prime. Right? So just looking at these combinations, you can immediately go to the continuous limit. So this is plus minus I omega naught t. Okay. Okay, so with these rules of the game, what you discover is slightly unpleasant, but I will write it anyway. My plus, my minus is called G less T prime, and this thing is rho 1 minus rho prime, and then T minus phi minus plus T prime. It is called G larger. This. So notice that this is a pure zero mode of my operator. Here it is. And then there are two things where diagonal is located, namely phi plus phi plus. And this is called time-ordered green function, precisely because there is a difference above diagonal and below diagonal. So depending whether t larger than t prime is, you have one answer, t smaller than t prime, you have another answer. So, and this is theta function, t minus t prime, g larger plus theta function of t prime minus t g small. And then there is phi minus, which is called anti-time ordered function. I will not write it down. So, so a few things. So first of all, it's a good idea to think about these green functions as a matrices. So there is an obvious sort of 2x2 structure here, but that's not what I have in mind now. I mean matrices in a time space, because they, after all, they came from here. This is a matrix in a time space. That one remark, another remark that these continuous notations are almost okay. Yeah, by the way, notice that this is nothing else but Bose-Einstein distribution function. So this is just occupation number of my harmonic oscillator. And this is 1 plus. 1 plus, 1 minus, yes, 1 plus. Now, continuous notations is almost good and rigorous, but there is ambiguity about theta function in coinciding times. Essentially, this way of writing things doesn't tell you much what happens exactly at the diagonal. Right? But if you look at the discrete representation, you do know exactly what happens at the diagonal. So it's not that you don't know, but it's just slightly hidden here. Right? So in the notes you can find, painfully long discussion of what exactly happens there. So I don't want to repeat it. At the point where I will need it, I will mention it. Okay? But remember, there is some words to say about diagonal here, coinciding times. Okay, good. Now, that's actually notations in which this famous Kadanov-Bain book is written, and many people use it. To my taste, it's still a little bit too complicated. At least I don't have much intuition about that. Now, what Keldysh essentially noticed is that it is slightly excessive representation. Why? Because there is a linear relation between these 4 green functions. They are not independent. Simply by looking at it, you realize that if you sum up, okay, I should write it down probably, otherwise you will not realize. Okay. Larger. Yeah, so if you sum up these two, then look what you got. You have theta t minus t prime and theta t prime minus t, and it's 1 everywhere, but on the, okay, with ambiguity about the diagonal. So you get G larger. same here, you got G smaller. So simply if you take GT plus GT anti-order minus G larger minus G smaller, you got 0. Yes. Again, it's actually not true on the diagram, but that's not a big deal. So we'll hopefully discuss even why it's not a big deal. But say for the diagonal, everywhere else, this is true. Okay. And that suggests that you better somehow explore it and not keep always 4 green function, but somehow rearrange them. Right? And this is done by introducing new fields. Instead of fields living in the upper and lower part of the contour, you want to introduce the linear combinations. So one is phi plus phi minus. And you call it phi classical. And we will see in a while why this is not a crazy notation. Square root of 2 is just a minimization. And then the second linear combination, naturally minus square root of 2, you call phi quantum. Okay. So now those are my basic objects. So I will, the entire theory will be formulated in the setting where all degrees of freedom are doubled, but they are doubled in this particular way. There is a classical part of the field and there is a quantum part. Classical is the one which is the same on the both, let me put it this way. If by some reason phi q is equal to 0, so you have purely classical thing, then you see it means that it is exactly the same on the upper and lower quantum. Right? And remember we discussed yesterday that this is exactly what you want from your external classical fields which you apply to your system. Right? Those are such that they don't have base, they have purely base. Right? But quantum fields, which are living inside quantum mechanics, we are doing functional integral here, so we integrate from minus infinity to infinity, independent with phi plus and phi minus, so there is no actually any reason to think that this is equal to this. They are hidden. So therefore, this thing somehow knows about the fact that, about quantum fluctuations, about the fact that we are doing integration instead of limiting ourselves to some specific configuration which is the same up on the up and down part. Okay. Now, one word of caution. When we will go to classical theory, classical stochastic theory, this thing will still play a very, very important role. So despite of the name quantum, it actually also knows about purely classical stochastic fluctuations. Right? So it's responsible for fluctuations. All right, there's it. So those are just linear combination and no correlation function of initial fields. So we can just read out correlation functions of this field. Right? So you can write out phi alpha t phi beta t prime, where the synthesis alpha and beta run between classical and quantum. Okay. And this is a matrix in this classical quantum subspace, which is actually precisely a part of the flavor subspace in Nightland notations. This is my flavor, which is part of it, and it looks like this. So first of all, this element, namely quantum component, is 0. So so where quantum fluctuations are uncorrelated. And that's precisely manifestation of this. So just linear algebra shows you that what would stay here is nothing else but that linear combination of green functions. Okay, and it is very good. Now, what stays here is called G A. Advanced. What stays here is G retarded. Right. And there is something here. So these now are three basic objects: retarded, advanced, and Keldysh. And everything which what we are going to do will be rotating about these three objects. Okay, now who are they? So let me just tell you. So retarded is theta t minus t prime, g larger minus g smaller. Advanced is theta t prime minus t, g smaller minus g larger. And what I call Keldysh is simply the sum of them. Now, the reason why it's all written in terms of smaller and larger and not in terms of t and t theta, because I already incorporated this knowledge. Okay. Right. So the important thing to notice is that these two guys are triangular matrices. And I never remember who is who. Maybe it's written here. Yes. So retarded is a lower triangular matrix. It has something here but zero here. Advanced is upper triangular matrix. It has zero below the diagonal. Something above the diagonal. Now, diagonal by itself, strictly speaking, is not zero. If you do this exercise, you will see that it is not. But what it is true, it is the holy line. So what is true is that G retarded of t plus t constant is zero. Right. Now, naively, you would, you know that if you have a purely retarded function and you do Fourier transform, if everything is time translation invariant, as it is in my naive example, then you can go to a Fourier transform, and since it's a retarded function, you function in the entire upper half plane of energy. Okay? So you can say that G retarded of T is integral f G retarded this on much so not, something like this, minus plus I zero, and there is a sort of temptation to say, okay, it's an analytic function in upper half plane, so let me close the contour like this, and then it will be zero. Okay? Now it's almost true, but it's converging at infinity. So this is not actually a kosher thing to do. So it's actually not zero, it's whatever, I pi, minus I pi. And then advanced is opposite of that. Yeah, one second. And the sum of them, it's only the sum of them which is zero, in which the integral is convergent actually. But the nature is good to us, and you can show that they always, if somewhere you have green function at coinciding times, you can be sure that it will never come alone. It will always come in pairs. Okay? So therefore, as a rule of thumb, you can say that this is zero, and that's practically never a mistake. I don't know a single example where you would screw it up if you do it. Okay? But you should be careful. Yes?
So can I do this integral before taking t to t prime? There will be an exponential. And later, after taking integral, take the limits.
Hmm?
After taking integral, if I take the limits, am I going to find 0? T goes to T prime.
Well, look, since depending whether it's larger or
Let's say
zero.
T,
So in one case you have to close your contour above, in another case you have to close below, so therefore the limit from one side is not the same as the limit on another. So precisely the same ambiguity about what is theta function at coinciding times. It may be anything. And to know what it is, you actually need to play with the discrete representation. At least I don't know any other way to decide it. All right? Good. Now, there is another very useful observation is that if you have a bunch of retarded, let's say, function of t prime, and you multiply it by retarded of t prime, t double prime, and retarded t double prime, t triple prime, what you get in the end is still a retarded function of whatever t and t triple prime. Okay, so that's simply coming from the fact that multiplying triangular matrices, you always get a triangular matrix.
Do you need to integrate over the interior variables there?
Yes, the multiplication of matrices means that you do a convolutions. Or again, if it's translationally, time translationally linear problem, then you go to a frequency space, it's just a multiplication, you multiply functions analytic and upper half plane, you still get analytic function in upper half plane. But one second. But what I'm trying to say that this property goes beyond equilibrium. You don't have to rely to time translational invariance. It may be any dependence on t prime and t double prime, completely crazy. Still, this will hold. Okay, because this guy is always a triangular matrix. Yes, there.
I was going to ask, is that's the property ultimately goes back to commutative commutative relation, or at equal times you get a
This one,
yeah.
no. What goes back to commutation relation is the fact that g retarded of tt minus g plus of tt is 2 pi I, minus 2 pi I don't remember. That follows from the commutation relation.
What's this?
This one, I don't know what's the underlying cause. For me, it's just that. Something else? All right. Now another observation again, which is true much beyond my idiotic example, is that if you look at it as a matrices, then advanced matrix is G retarded cross in a sense that you have to change time arguments. T goes to T prime goes to T, and whatever metric structure, spin or whatever you may also you do Hermitian conjugation. So that is a holy thing. So in some sense, they are not independent matrices, they are just a repetition of one and the same information. Okay. Now, finally, this guy is something else, and that's the main difference between equilibrium situation and non-equilibrium. So let me tell you a few words about this guy. Right. So now, before I do it, let me just tell you what it is for my simple example. So this one, as we already said, is epsilon minus omega naught plus I0. This one is epsilon minus omega naught minus I0. So roughly speaking, these two things carry the information about spectrum of your system. Right? So it has poles of zero mode at the point where the system has a level, okay, energy state. Now, of course, if you have an interacting system, the spectrum itself is getting normalized and depends on occupations and probability distribution, density metrics. But roughly speaking, this thing always store the information about true spectrum, normalized in some sense. Okay. Now this thing is about something else. Again, in our simple example, it's nothing but 2 pi I 2 Bose distribution function plus 1 delta function of epsilon minus omega naught. Okay? So it again knows something about the spectrum, so it's heavily peaked at the spectrum, but the weight of this function knows about, in this case, Bose-Einstein distribution function. Right? So this thing is something which carry information about distribution functions, about whether things in equilibrium, non-equilibrium, how it evolves. We'll talk about it. Right? Now, so you can notice that that at least in our simple example, this thing being transformed to energy representation is hyperbolic cotangent of epsilon minus mu of 2t. This is nothing else but this combination. It's a hyperbolic cotangent. Yeah. And we used to be rho naught 1 minus rho naught, and rho naught used to be e to the minus beta omega naught minus e. Which another way of writing it is okay. Now that suggests to parameterize this thing in a completely general setting in the following way. So you have GK, and again it's a matrix dependent on 2 times. So what I'm writing now is a matrix multiplication. A retarded matrix times some matrix F minus matrix F becomes this. So just by playing with the symmetries, yeah, first of all, this is anti-Hermitian matrix, right? And you can show that using Hermitian conjugation between R and A, you can show that you can always parameterize it with the help of a Hermitian matrix F. So F is a Hermitian matrix in a time space. Okay. Now again, in our simple model, this F is nothing else but this. Now, the statement which we will somehow emerge today is that this property that F is nothing else but this is not restricted to our simple model, but it's a generic property of equilibrium systems. Okay. And this statement is called fluctuation dissipation theory. So there is a relation between green functions, in this case between, in my representation, between Keldysh green function and retardant advanced green function, which is wholly for equilibrium setup. Okay? By the way, that's story for bosons. If you will do fermions, then instead of cotangent, you will do tangent. But otherwise, this story is still there, right?
So can you use the second line GK GRF minus FGA for non-equilibrium systems?
Oh yeah,
all the
yeah,
time?
yeah. That is general. Okay, and then what we know that in equilibrium, no matter what, this F have to go to this one. Okay, so what we will do in a few minutes, we will write kinetic equation, which will be equation for this matrix F. And we will sooner or later convince ourselves that this thing is always a stationary solution of this kinetic equation. Of any kinetic equation. Yes.
Can you say a little more about how this is equivalent to the fluctuation dissipation theorem? I'm missing the philosophy of it.
By definition, this is a fluctuation dissipation theorem. But if you have a different definition, then what it is.
Okay, well, okay, so let me, or I'll ask afterward.
It's so basic theorem that there is an infinite many formulation, like second law of thermodynamics, right? They're all equivalent. So.
What parts are connected to fluctuations and which are dissipation?
Very good. What part is fluctuation? So this thing knows about equation of motion, which will, and we will derive it very, very explicitly, include dissipative tails. Okay, so where is it? So far it's equation like this, which is purely non-dissipative. If you include some buff and you integrate it out, this type of equation will include dissipative tails. Okay, so therefore this thing knows about dissipation, and this thing is explicitly about amplitude of fluctuations. But don't worry, it all will come painfully explicitly. Believe me.
The zero over there, QQ, presumably at equal time is not zero. Is that something you're going to address?
Yes, it is indeed, as I said, this relation is not
Right.
true with equal time. Yes, it will come up in some way, yes. Right. Okay, let's see where you are now. Good. So we introduce new variables. So far it's a pretty formal trick. And we know what's the correlation function, and I sort of promised you some generalities in this structure. So now what we want to have a continuum theory of that sort, right? But first of all, written not in these old variables who has ugly correlations, but in these new variables whose correlations are a little bit nicer. Okay? And then we wanted to be sort of free of this need to resort to discrete representation. We want to know how to resolve ambiguities. Okay? So therefore, let's try to write an action in terms of these classical quantum variables now. So what we want to have is that this phi alpha, phi beta, there again alpha and beta are from now on they always classical and quantum. I will never resort back to phi plus, phi minus, they're gone forever. Good news. So the bonds are right. Quantum, and they're complex conjugates, of course. And then some action, written in terms of now what do we know about this action? So for our simple model, we at least understand that this is a quadratic form. Right? So we still don't deal with any interactions. So it's a quadratic form, which is dt prime in the most general way. Then quadratic form now this is a some quadratic form, which is a matrix again in TT prime space. Now what do we know about it? Yes, well, what we know is that by inverting this thing, we're supposed to get exactly that. That's by definition. So therefore, whatever's sitting here, the operator in the action, is nothing else but inversion of this thing. Okay? So therefore, let's try to invert it back. So I'm sort of doing convoluting procedure. I'm starting from the action, invert, getting green function, rearrange them, and then inverting back to get the action. It's a little bit idiotic, but it will sort of show what the structure of an action should be. So. So I'm writing this thing. Okay. So first of all, you immediately realize that this thing should be 0. Okay. Because what you want baseline times baseline to be 0. So that should be 0, precisely in the same way that this is 0. So that's just how long it is. And then you realize that whatever is sitting here is simply inverse of that. Right? And this is a triangular matrix, and the inverse of the triangular matrix is again triangular matrix. Right? So this is GR to the -1. In the same way, whatever is sitting here is inverse of that, and again it's purely triangular matrix, so it's GA to the -1. And whatever is sitting here, let me call it Keldysh component. Okay? There is one line of calculation to calculate what it is. Right? So you multiply this matrix by this matrix, and you require that this is a unit matrix. So what you find is that this thing has to be. Yeah, yes and no. There's things like this on the table. I don't know how good is it. Let's try it. So this is minus. Oh, well. GA -1, which is after simple algebra, you can show it. This is F minus F GA -1. Okay. Now what it is? So we know that this guy is 1 over epsilon minus 1 in the naught. You invert it, you got epsilon minus 1 in the naught. And if you go back to time representation, this is IDT. Okay. Same here. It's IDT. But they should be properly normalized. You should understand, and it's sort of still important to remember, that in a discrete representation this would be almost diagonal matrix. Time derivative is something which is 1, 1, 1, 1, minus 1, minus 1, minus 1, minus 1. Right? All this thing can be above the main diagonal. Right? So what you should acknowledge is that in this case it's below the main diagonal, in this case it's roughly, say this is minus and 0, this is plus. That simply tells you what is a regularization. If you want to give it to a computer and you want to put it in a discrete time, the way to discretize this time derivatives is actually opposite. One is retarded way, another is an advanced way. Okay? Good. now this thing, if you just take it as it is, so here is time derivative, here is cotangent, and that's precisely the same. Okay? So it's seemingly zero. Right? So for our simple example, what you got, strictly speaking, here is 2I0 times f, because everything else comes. But you should understand that this 0 and this 0 are very different zeros. So this 0 will cease to be 0 in the moment we include interactions of anything else in our system. So this is a completely idiotic consequence of our super simple model. Okay. On the other hand, this guy is sort of a holy zero. Okay. And it will stay there whatever we do. Okay. And it's important to check that it is indeed keeps staying zero, otherwise we are in trouble. The same is true about retarded and advanced nature of these guys. They also will remain retarded and advanced no matter how we normalize them, what kind of corrections, whatever. But no matter what, they have this retarded and advanced nature. Okay. So that being said, now I can write down this thing, so this is 0, g minus 1, once g minus 1, retarded, g minus 1 retarded. With this understanding, so this, it just tells you what's the right way to invert this matrix. Okay? So now, looking at it, you understand that there are a few generic properties, and as we go, we will uncover more. So let me just list them.
Is F general there when you got 2I0 F? That's a general F, or is that for?
Look, what is going to be in a moment, and I hope it helps. So it will be self-energy. This one will be advanced, this one will be retarded self-energy, and this one will be another self-energy.
Well, that's after you're in all but
After you do something, something meaningful.
For this single oscillator problem.
Yes.
You know what you
For oscillator problem, it's just regularization, which tells you how to invert this matrix.
But for that, you need to look at discrete matrix.
Right.
Is that right?
Right.
Otherwise, you just get 0.
Right. If you are very naive, you just, you start from this, you do linear transformation of your phi plus, phi minus, like this. Okay? It's one line iteration, I don't have to go through this. So all you get is I dt minus omega here,
Okay, there's nothing else there.
here, and then that's it.
Right.
Right, so precisely the reason I went for all this pain is to say that it's not that simple. So this thing and this thing has a very different status. Yes?
What about the determinant? When you find the inverse of the matrix?
Well, look, they check that determinant is okay. Right? They did it explicitly. Yes. Yes.
Yeah, but you have to divide
Right.
by the determinant in order to get.
Right. So I guess what you're saying is that no. Well, to a zero approximation, you can say that this is determinant of this and determinant of this. Minus.
But you have to divide your whole matrix by the determinant.
If you
with
just
the inverse, correct?
If you just multiply your green function very into the next function, you can verify that it'll give you 1. So
Right, so if you want to avoid inverting the discrete guy, you can just start with a, you say, I have a free theory and I know what I know what I want for non-interactive propagators and non-interactive components, GK, GR, JR, those are well defined, and they're not infinitesimal. And then you just invert that in a continuum.
Well, look, it's not the first time I'm trying to tell the story, and I tried many different ways. That's the one which I came up with. I'm sure there is a better way to say it. Right, but so let me list the essential thing. So first of all, the classical component in the action is 0. Okay? Now this is, as I said, is a holy thing, and it's sort of very close relative to our normalization z equal 1. Now what it comes from is from an observation that is if your field is purely classical, right? So if your evolution on the forward contour and the back contour are exactly the same, phi minus is equal to phi plus, that means that it's a purely classical field, and that's the only component, then this is the only component which is left. But it has to be 0, because there is no any phase gain, right? If you do precisely the same field on the forward and the backward, you develop some phase and then you unwind this phase. So you expect that if your field is purely classical, phi quantum is equal to 0, then you expect that your action quantum, if this guy is 0, then the action should be 0. And that's simply coming from the fact that whatever you gain here, you undo. The ring should be unbound. Okay, so that's the first observation. The second observation, that classical quantum and quantum classical components are mutually dilution conjugated. Triangular matrices. And this triangular structure is responsible for the causality of the response. You will see that they will always play a role of response functions. Okay? And the fact that you expect response to be retarded, in some cases advanced, but in any case causal, is sitting in this state. Okay? And since I claim it is a generic statement, we will check a couple of times that no renormalization can violate this statement. Okay, good. And finally, the quantum component, which we will see is responsible for this one, is responsible for fluctuations of thermal and quantum. Okay. It is anti-Hermitian matrix, generic. Which knows somehow about distribution function. This f function, where is it? Is hidden precisely in this QQ component. So the distribution function knows about fluctuations. Okay? Good. So this is sort of generic structure which we uncovered in a very toyish model, but I'm claiming that it goes much beyond of it, of course. So now it's probably time to go to something else. I mean to go to real fields and introduce interaction and move. But before we do, please ask questions. Yes.
Can you say again maybe why the classical part of the action is zero? It's something you're saying that when there are no fluctuations.
No, that's simply. Look, what I'm saying is classical equals zero means, no, but quantum equals zero, right? Means phi plus equals phi minus. Then you see it must be zero, right?
What if I ask you this question? What kind of a system would have no quantum part? Would have only classical part?
The one where you neglect all the fluctuations.
Okay. So if I have no fluctuations, should it be really obvious to see that the action is zero?
Yes. Because that's, no fluctuation, you sit in the minimum, you don't gain any action.
Well, the forward and backward cancel.
Yeah.
That's the one. No, it
Some action along each path, but they cancel.
Yes. I mean, it's probably will be easier to seeing examples where action is manifestly not zero. Right? So I will show you situations like this, and then you will see what all this is about.
It's a little strange, I mean, it's related to the comment that just made, the question was that, suppose you have fluctuations along forward contour, and then you have exactly the mirroring fluctuations in the reverse contour. You would think, you're really doing something different than just solving a saddle point equation, a classical equation, because, there are fluctuations in the forward contour. You're really summing over phi pluses and phi minuses, but doing it in a correlated way that they're equal to each other. Why does that correspond to no fluctuation? I mean, it's some kind of fluctuations, but maybe for the density matrix.
Look, it's pretty, yes, it's pretty much about this. So you're doing about dp on x, right? From minus infinity to infinity. Right? So p fluctuates like crazy. And the result of it is the date that x is sitting full. So you need something like p squared here, minus. And that's precisely analog of this part, which will tell you that you can deviate from the data.
Okay.
So it's really pretty much that state. All right, let's move. So when am I supposed to shut up? From the bottom of an hour? Or?
Well, half an hour.
All right, so let's go. So let's now think that we have many oscillators. They characterized by the set of frequencies omega k, where k is some index, for example, momentum. If you wish, you can think of this as phase to m. So then your action, again, in the Keldysh contour, you will have to write as sum over k t phi k times t minus omega k. That is a simple part. Now we may want to do a Fourier transform, and instead of just formal index k, so instead of keeping phi k of t, we can go to phi of t and r. If it's uniform system, it's going to be sum over k e minus r. then you will find fields in the real space. So then this non-interacting part of an action will give you dt and dr. So if I go to classical and quantum fields, I will write it as dt and dr by classical and quantum in this matrix with my poly zero here. Equation of motion essentially sitting here, advanced regularization here with the target regularization. Something here, which is so far is a pure regularization, but in a moment we are going to make it more meaningful. And then okay. So that, of course, still not very interesting story. So we want to make it somehow interact. Now, so far it's bosons. So yeah.
I want to understand the way that you've been talking about matrices. It seems like doing this contraction of those three matrices is equivalent to doing the time integration. So that really I shouldn't be writing the time integral there.
Here.
Because it's essentially, I'm thinking, a time matrix and contracting and all the indices, that's doing the time integral. I don't understand why that's.
No, look. This is a quadratic form. So this is a matrix T prime, vector of T, conjugated vector of the vector of T prime, conjugated vector of T. And you do convolution T and T prime. Now it so happens that their equation of motion are local in time. So, or almost local in time, they have time derivative. Right? So this T prime matrix is actually almost delta function IDT.
You're going to just ask this a slightly different way. When I discretize my time
Yes.
contour,
Yes.
then you've been writing these products of matrices. If I were to do that, then is it correct that I would eliminate the integral over dt in favor of kind of using this matrix notation? Where I call, for example, the retarded Greek function this upper triangular matrix. I'm trying to understand the different notations you're using and how they.
Right, look. It's 2n by 2n matrix.
Okay.
This is 2n vector, this is 2n.
If I write it
Conjugated,
like
yeah.
that, then I would eliminate the integral over time, right?
Right, so instead of
That's all I'm asking.
writing summation from 1 up to 2n, I'm now sort of using a shortcut notation.
Summation is taken for you by doing this matrix product.
He's explicitly writing that.
I'm not sure what. So let's.
He just means that-
Convention, you don't have like Einstein summation convention, you have to write those sums explicitly. That's it, and then
He's
you have to
writing-
write those integrals explicitly as well.
We'll talk later. Sorry, I was trying to. We'll talk later.
Yes.
He
So,
just doesn't
sorry,
want
I'm too slow to react. Right. So now the simplest interaction which you can imagine that cold atomic people, for example, like is just local four bosons interactions. So you want to say that this is some interaction constant which is related to whatever S-weight scattering length, whatever it is, dt and dr phi bar
three part question maybe.
Yeah.
So, this omega k is k stable to m, now you Fourier transform it and you get minus or plus? You get plus.
Minus or plus? That's a good question.
I would say plus.
That's a good question. I wouldn't bet on it. Plus, you're right. Yes. Right. Good. Okay, now this is still on my Keldysh contour, so the next step I have to write it as from minus infinity to infinity dt dr 5 plus 5 minus oh, plus minus 5 minus right? And then you substitute this linear transformation and you do two lines of algebra. So you end up with g over 2 dc dr, and what you integrate is phi plus phi quantum. Oh. Okay, let me write it down then. Well, I realized that I screwed up and I had to introduce diagrammatic notation. Right, otherwise, what we are going to do now will be incomprehensible. So this matrix green function, so let me step back and introduce some notations. Classical field we will denote as full line, and quantum field we will denote as dashed line. Okay? So then what your green functions are correlation functions of two fields. So then what you have to say is that a retarded function t prime being phi classical, phi quantum should be represented as object like this. The advanced green function being phi quantum, phi classical should be represented as an object like this. Finally, the Keldysh function being phi classical should be represented as just one free line. Okay, and finally 0 is fully dashed line. So fully dashed line does not exist. Okay. So that's notation. So now why I'm bringing this notation, because now whatever interaction you invented in your system you go for this simple algebra, you write it as phi plus minus phi minus, you do linear transformation, you get something. This something looks ugly, but it becomes much nicer if you draw it simply instead of writing it. Right? And the drawing is like this. So you have a vertex with 3 classical fields. In any case, there are 2 incoming fields, 2 outgoing fields as in any diagram. And you have 2 types of vertices. Either you have 3 classical fields, 1 quantum, or you have 3 quantum and 1 classical. So basically you have 2 types of vertices. One is like this, and another is and there are complex conjugation means the same but with inverted direction of all errors. Okay, so that's our objects to play with in a moment. Now notice that again this Holly property, which I stupidly erased, is classical 0 is equal to 0. So the moment I put quantum field to be 0, everything is gone. Okay. Simply because of the same very basic fact that the way I generated my action, I subtract opposite quantum from the forward quantum. So if they are the same, the thing must be 0. So you can sort of immediately deduce from here the statement that this bare action is an ordered function of phi quantum. Okay. Now this is not a Holly property, this is a property of having time reversal invariant. Because time reversal invariance will interchange forward and backward contour. So it will change Q to phi quantum to minus phi quantum, so your actions should be ordered function. Now once they integrate out some continuum of degrees of freedom, like above, okay, we'll find an effective action which is not an ordered function of quantum component, and this action will already knows about the direction of time. It will not be. Yeah.
But the same statement can be made for classical, phi classical.
Yes and no, because would I take phi cube interaction instead of phi to the 4? That would not be the case anymore.
Oh, I see.
So this is a complete accident.
Okay.
Classical is about classical equation of motions, and they be even or odd depending what kind of nonlinearity you pick there. Okay? Good. Now what? Yes. And now, so the next step, I will want to develop perturbation theory. But before you develop perturbation theory, you ask yourself, I expand, but I expand on top of what? Right? So what is a 0 point of your expansion? Right? So what's the answer? What you always expand?
E equal to 0.
Yeah, but that's sort of a very particular case. It may be true sometimes, but maybe not.
Some saddle point?
Right. So if you have an integral, the first thing, the exponential integral, right? So the first thing you're supposed to do, you're supposed to look for saddle points, and actually maybe more than one saddle point. The situation is very interesting. Once you find the saddle point, then you can start doing expansion around the saddle point. Okay. So before you even start doing perturbation theory, you should ask question about saddle point. Okay. So therefore, the step number 1 is discussing saddle point. So how do we discuss saddle point? You take variation of your action, whatever it is, with respect to your field. And in this case, we have two fields, classical and quantum. So we have to take variation with respect to both. Okay. So the first thing to say, we take D as quantum field of R and C. Okay, so there is this linear part where you have things like quantum and classical, right? For example, this one. Or there is an opposite one, but by doing integration by parts, you can immediately see that this is sort of up to factor of 2, which I'm going to screw it up. They are the same. So what you find is IDT plus radian square R 2m equal 5 classical. And so that's from here. In principle, you have something coming from here, although it's a pure regularization. Something like 4 on 0 on quantum. That's a pure regularization. We shouldn't be too much concerned about it, at least not yet. And then you have this interaction thing. So you can take this guy. Actually, I should take variation with respect to phi bar quant. Give you a good citizen. So then I have this thing, which is my interaction constant G plus or minus, I would say. And then I have finally another piece, something like and then I have another equation. Yes, phi classical. Yeah, by the way, notice that this is sort of retarded time derivative. So it came from, if you look carefully, it came from this piece which had retarded derivatization. Now, if you take variation with respect to classical field, you've got oppositely moving equation. And then a bunch of terms. Yeah, I should. Okay. Quantum and then quantum square, like plus. Something like this. Now another thing which I sort of better add, I may have a classical potential here, B classical of R, for example, trap, right, where my F and D just for the sake of generality. So when this external potential will propagate here, into here.
The last one there should be quantum, fiber quantum.
Yeah. Okay, so now it's Horval equations. They're coupled in principle, right? And in some very interesting cases, and actually I'm pretty sure we'll come to such cases, you have to think about solution of a couple of equations. But you have always sort of a fallback, and you can always find a solution where phi quantum is equal to 0. Okay? Now, why is that? Because of your Pauli thing that if phi quantum equal to 0, the action should be 0. Right? What does it mean? It means that if you think about this action as being polynomial in phi quantum, it doesn't have 0 power in this polynomial. Right? It always comes from 1, 3, whatever, higher powers. Right? So now you take variation with respect to classical, it's still a polynomial in quantum which starts from the first power, never 0 power. Okay? So therefore, if you take this, it will be always a solution. Okay? It may be not the only solution, it may even not be a solution you're looking for, but it is a solution.
But it will not satisfy the first equation.
No.
So,
It is a solution, and for this thing to be a solution, you have to and then you will have equation for the classical component, which is, or miracle is just Gross-Pitayevsky equation in this case. So Gross-Pitayevsky equation is an example of a classical equation of motion. Although you may think about it as being quantum, but it's actually behavior of an entire condensate. So it is it's essentially a classical saddle point equation of your quantum field theory. And it emerges here as a particular case of a saddle point equation, namely particular saddle point equation where you restrict yourself to a situation like this. Right? And it's actually completely, again, generic statement that among your saddle points, you can always find one. I call it classical saddle point. Okay. Such that phi quantum equals 0 is a good idea, and then phi classical does something. There is equation of motion. It may be Newton equation, it may be Dostoevsky equation, it may be diffusion equation, something, right? Which you have to solve. Okay? So 90% of physics is done, or the perturbative physics is done as an expansion around such classical saddle points. Okay? Now the good news about this saddle point is that since phi quantum is equal to 0, you know that the action at this saddle point is identically 0 by definition. And therefore, at least with exponential accuracy, what you calculated your z, e to the I s, and s is equal to 0, is equal to 1, as it should be. So, again, I'm sloppy about the factor. It could be complicated, but believe me, it's not. So, this classical saddle point entirely takes care of the normalization. Okay? Now, for example, the perturbation theory which Alex Franklin was doing this morning, it's precisely an example of expansion near one of such classical saddle points in a sigma model there, and you got this 1 over s squared result, right? Now, you also wonder what happens with cosine of 2x. So you can obtain this cosine 2x as an expansion near another saddle point which is not constant. Okay? And then this thing, e to the I s, is actually plus minus I s, is actually action at this non-trivial, non-classical saddle point. Okay? But that's already sort of more complicated business. So I'm just telling you that there are other saddle points. They don't contribute to normalization, but they do contribute to observables. And sometimes if you want to find interesting effects, like oscillatory part of the level statistics, you have to take them into account. But if you are doing sort of old-style Russian whatever diagrammatic technique, then you're good playing with this. Okay. Now,
Can you comment on why this oscillations come from non-trivial saddle points? What's the physics of non-trivial saddle points?
in this particular case.
Yeah, I mean, somehow you have this quantum field, but there's a non-trivial value that
Look, I don't have a good answer. It's all.
Is there another example where the
Yes.
other saddle points
Oh
are
yes,
somehow
oh
very
yes,
simple?
and I will.
Describe?
There is a trivial examples, like if you want to describe thermal activation from from a Kramers escape from
Oh, okay.
quantum, right?
That would be another set.
And then whatever you're looking for is e to the minus height of the value divided by temperature, and this is precisely the action on a non-trivial saddle point, non-classical saddle point trajectory.
It'll have a phi quantum non-zero.
Right. And this one I will
This you're
work.
going to talk about.
This I will work out completely explicitly. So,
Okay.
but
okay, that's good.
ask Adrian here.
No, but that's always helpful to have a simple example where it's
Yes. Now I'll give a simple example. Level statistics. I can push it around, but it will not helpful. All right. So good. So probably I shouldn't. Yes.
This distinction between DT R and DT advanced, is it in practice?
Oh, yeah.
Keep it, or?
Oh yeah. So yeah, and classical people know it very, very well. So if you look for some probability of rare events in statistical mechanics, you should solve analogous system of coupled equations. And one equation you should propagate forward in time, and another equation you should propagate backward in time. Right? Again, I will hopefully arrive to a very simple realization of this. But that's true. I mean, it's unavoidable. I don't have a good explanation of it, but it is an unavoidable feature of non-equilibrium statistical mechanics. Okay, so now let me just summarize a few things which I think are essential, which emerge from this discussion. So we sort of, I hope to learn build with actions, Kelvish actions, which live in a color subspace of two subfields, two fields. They have several generic properties, namely if you put this quantum component to be zero, it will be always zero. And this property, at least in the saddle point level, you immediately see that it is very close relative to our Hoyle normalization of the partition function. Now, the saddle point emerges as ds or d phi quantum, or ds or d phi classical. So this one, variation with respect to quantum component, give you classical equation of motions, in particular Newton equations, is precisely an example of such an equation, and this is why I'm saying that Newtonian mechanics should be introduced as a set of classical equations. So this one you can always solve by assuming this, but sometimes you should not be content with this, but you should go for less trivial situations, especially if you want to find some tails of some probability distribution functions or some oscillatory terms in level statistics. There are other examples. Now, so the quadratic forms, which are the form of a retarded operator, phi class. So in some sense you can include this nonlinear thing. You can include it into this operator. So altogether what you have is a construction where you have phi quantum, some classical retarded operator, Gross-Pilaevsky operator, which is operating on a classical thing. Right? And then, in principle, you have terms with higher order of phi quantum, 2 or 3 or whatever. So in our example it was 3, not, which are responsible for.
You said it had to be on. Did you say it had to be on in phi q?
Very good. It has to be odd, as long as T invariance is preserved.
Okay, so when you break time reversal invariance, you're going to get phi squared.
When you break it, you may have it even powers. And that's how immediately happens once you integrate out above. And these terms are responsible, as we will see, for fluctuations around this zero form. Whatever is not captured by Gross-Pilaevsky equation, whatever is left, quasi-particles are sitting here, but we'll see how it goes.
That's like the noise term and.
Yes, yes. In a classical context, this is precisely what is responsible for noise.
Do you get 0th power in broken?
No, that would
Yes, that's
contradict to my colleague's requirement.